In this section, we'll talk about the chain rule. You know what to do with the chain rule when you're in two dimensions. The calc 1, outside, leave the inside alone, then you derive the inside. So if you had something like tan of 4x and you were trying to derive it, the derivative of tan is secant squared, so you get a secant squared of 4x times the derivative of the inside. So that's the chain rule with one variable. What if you had two variables, and those two variables depended on another variable, like you had some parameter set up t? Then those x's and y's have a name. We call them intermediate variables. How do you do the chain rule then? Well, let's look at it as z equals f of x, y. So this up here is just a chain rule in two dimensions. dy dx is the derivative of y with respect to t, and then derive the inside. So the outside, inside. All right, let's take a look at our tree diagram. This is going to be tremendous, don't you worry. Let's start with some function z equals f of x, y. We've got two options when we take the partials. We could take the partial derivative of z with respect to x, or we could take the partial derivative of z with respect to y. If we take the partial of z with respect to x, now we have to derive x with respect to t. When we take the partial of z with respect to y, then we need to derive the y with respect to t. Now you notice that I'm going to try to make my curly cues go in the right spot. These first ones are both partials. The second ones are not partials. So the partial z with respect to x times the derivative of x with respect to t. The partial z with respect to y, derive y with respect to t. All right. What does this look like? Multiply and add. So if you've ever done tree diagrams for probabilities, you know you multiply the probabilities along the way. The same thing is going to be true in this case. You're going to multiply the partials together to get that formula. So what does the formula look like? Oh, I guess I never wrote it. All right, let's write it on the side over here. So when I multiply those things together that were on my tree diagram, I end up with the derivative of z with respect to t as the partial z with respect to x times dx dt plus partial z with respect to y dy dt. All right, and then I multiply those together and add them up. All right. Sometimes my answer will simply be an answer in terms of t. So let's take a look at this example here. We'll take partials and we'll answer with respect to t. All right, so I'm trying to find dz dt. Z equals xy squared is my z equals f of xy. The x is equal to t squared. The y is equal to t. I could be boring and throw the t's in at the beginning, but then that wouldn't help me to illustrate what the chain rule is. So let's try to do this with our chain rule formula. So dz dt is going to be the partial derivative of z with respect to x. So if I derive z equals xy with respect to x, then I'm just left with y squared, right? I'm taking it as a constant, times the derivative of x with respect to t. So now if I derive x with respect to t, good old power rule, 2 comes in front, power drops by 1. So partial z with respect to x, derivative of x with respect to t, plus the partial z with respect to y. So now take your xy squared, derive it with respect to y. So that 2 comes in the front, and I get a 2x times y to the first, because the power goes down by 1. What happens when you derive y with respect to t? Derive y with respect to t, and you just get 1. All right, so this gives me 2t times y squared. Here, I'm going to put this a spot for y squared, plus 2xy. Now I'd like to replace those t's, those y's and x's with t's. So the x gets replaced by a t squared, and the y's get replaced by t. Well, okay, so t is going to be squared, and that's a t here. Simplify. This will give me a 2t to the third. This will give me another 2t to the third, and I'll get 4t to the third. So that's how that chain rule works. Partial y, then partial x, then derive, partial y, then derive. All right, what happens when we have three variables? If you've got 3 intermediate variables, it works almost the same, except it's got an extra piece to it, doesn't it? If you want the partial derivative with respect to t and you've got 3 intermediate variables, same thing. Partial function with respect to the first variable with respect to the parameter. Partial with respect to the second variable, derive second variable with respect to parameter. Partial derivative with respect to the third variable, derive the third variable with respect to the parameter. So I've got this function here, and I'd like to work through the whole chain rule to see what I get. So q is the square root of x squared plus y squared plus z squared. I want to find the derivative of that, where x is the sine of t, and y and z are the cosine of t. All right, let's see what happens. I'm clearly going to have to come over to the side and get some work done over here. We started with q equals the square root of x squared plus y squared plus z squared. And so the first thing says, take the partial derivative of q with respect to x. Now, these things are all going to start the same way, in that q is really x squared plus y squared plus z squared to the 1/2. So when I go to derive that, I'll get 1/2 x squared plus y squared plus z squared to the negative 1/2 times the derivative of the inside based on whatever variable I'm deriving with respect to. Meaning that these things are all going to start off with me putting the derivative of the inside over the square root of that whole x squared plus y squared plus z squared. All right, so let's flesh this out here. The derivative of q with respect to t, right, that's our goal, dq dt, equals the partial q with respect to x. So it'll be a 2 square root of x squared plus y squared plus z squared times the derivative of the inside with respect to x. Well, with respect to x, the y squared and the z squared just become constants, and I get 2x. Okay. Now multiply that times the derivative of x with respect to t. If you go back to the original problem, x was sine t, and y and z were the cosine of t. So if I derive sine, I'm going to get negative cosine. No, I'm going to get regular cosine. What am I doing? Cosine of t. All right. Then I've got to take the partial of q with respect to y. So it's going to start the same way as before. 2 square root of x squared plus y squared plus z squared. This time times the derivative of the inside with respect to y. So I get a 2y on the top. X squared and z squared zero out. Now derive y with respect to t. So if I derive cosine, I'll end up with a negative sine of t. Okay, now partial q with respect to z. Again, it's going to be 1 over 2 square root of x squared plus y squared plus z squared. This time times the derivative of the inside with respect to z. So these first two go away. Derive the z squared, and I get 2z. Now, times the derivative of z with respect to t. Well, the derivative of z with respect to t is just negative sine of t. All right. What can I do? Let's try to simplify this a little bit. First of all, you notice all the 2's go away. All these 2's, 2 top and bottom, 2 top and bottom, 2 top and bottom. So I end up with x times cosine of t. Right? I'm saving this spot here for x. So x times the cosine of t plus y times the negative sine of t plus z times the negative sine of t all over my common denominator of the square root of x squared plus y squared plus z squared. All right, there's a z going over there. All right, let's fill in those x, y, z spots with the parameters up top here. So x is equal to the sine of t, y is equal to the cosine of t, z is equal to the cosine of t. A little bit of this simplifies. The top is a sine cosine minus sine cosine minus sine cosine. So don't these first two terms and those first two terms zero out? And I end up with negative sine t cosine t over. Now, what happens when I take those values and I substitute them into the bottom? If x is equal to sine of t, I'll get sine squared t plus y is equal to cosine of t, so cosine squared t, and z is also equal to cosine t, so cosine squared t again. These first two terms give me a 1. Sine squared plus cosine squared is 1. So under the radical, I just get 1 plus cosine squared of t. And that is the derivative of function q with respect to t by using the chain rule with 3 variables. So derive the first, derivative of the inside. Derive the second, derivative, partial third, derivative. All right, so all of these that we've done so far have been built on the premise that there's one variable that's an intermediate variable. So we've had derivatives with respect to t with 2 and 3 variables, but we've only had one parameter. What if we had something that was dependent on both s and t? What you'll end up then with is 2 partial derivatives. You'll get a partial derivative with respect to s and a partial derivative with respect to t of the same function. So let's slide over here and make a tree diagram. I'm going to make my tree diagram go down this time, so I think it's easier. Let's start with z up on the top. I've got 2 parameters in this function, s and t. So the first time I derive something, I can take the partial z with respect to y. The other option is to take the partial z with respect to x. From there, I can do it for each of the 2 parameters involved. So I can take the partial derivative of x with respect to t, or I could take the partial derivative of x with respect to s. So these are all partials. Over here, I can take the partial y with respect to s, or I could take the partial y with respect to t. So I first derived it with respect to x, and now I'm deriving the x's with respect to each of those parameters. On the right side, I'm deriving the original function with respect to y, then I'm deriving the y with each of those parameters. So we are going to end up with 2 answers, right? We'll end up with a partial derivative of z with respect to s as followed down the one side. You'll get the partial z with respect to x plus, now pick the one you want. If you want the s's, then you want this path over here, the partial x with respect to s. And that's actually a product, that's not a sum. The partial x with respect to s. Now you've got to add in the second half of that. What follows on the other side? A partial z with respect to y times, if I'm going to go down the s road over here, I'm going to go down the s road over here. So now I've got to do the partial y with respect to s. So I followed the path in the first formula to do the partials with respect to one variable, derive the one variable with respect to the one parameter. Partials of the function with the other variable, same parameter. The next equation is going to be the same thing, except we're going to do it with respect to t. So the partial z with respect to t is still going to be the partial z with respect to x, except this time I'll multiply by the partial x with respect to t, because that's what I'm working on over here. Then the next thing is, again, do the partial z with respect to y, except this time you'll do the partial y with respect to t. And now I got 2 different answers. two different partial derivatives. One for how it changes with respect to the parameter s, one for how it changes with respect to the parameter t. Which means our answers could get a little funny looking. It's okay. All right, so we drew the tree diagram. That was great. This is the formula written out a little bit nicer than I wrote it, right? Z's with respect to x, x, and s. So the first line across are all the partials with respect to s. The second are all the partials with respect to t. All right, so that's in the PowerPoint. You can see it written out nicely. Let's take a look at this one here. This one is, I want the partial with respect to x, or with respect to s, and the partial with respect to t, where z is equal to xy minus 2x plus 3y, and I've defined my x's and y's in terms of parameters. So let's start this rule in terms of x's and y's, and then we'll move on from there. All right. Let's take the partial z with respect to t. Partial z with respect to t is going to be the partial z with respect to x. So if I derive this expression here with respect to x, the derivative of this first thing with respect to x is just y. Derive the second term with respect to x, and it's just negative 2. Derive the third one with respect to x is just 0. So there's your partial derivative with respect to x. Now you've got to derive x with respect to t. Right, so here I'm going to take the partial derivative of x with respect to t. Well, notice what x is. X is the cosine of s. There's no t in there anywhere. Turns out that if you derive it like that, you just get 0. Now what do I have to do? Take the partial z with respect to y. So in this first term, I just get an x. The second term goes away, right? There's no y's in there at all to derive. The third one with respect to y just gives me a 3. So that times the partial y with respect to t. Well, now there is going to be a derivative. The partial y with respect to t is cosine of t. All right, so what does that give me? The first piece goes away, and I end up with x plus 3 times the cosine of t. If I can answer in terms of s's and t's, I will. So I'll end up with a cosine of s plus 3 times the cosine of t. And that looks like that's as good as it's going to get. All right, what do I have to do for the second one? For the second one, I need the derivative of z with respect to s. So the derivative of z with respect to s is going to be the derivative of z with respect to x times the derivative of x, and this time with respect to s, and then dz dy times dy ds. Now you realize the first two answers are going to be the same. The derivative of z with respect to x is still y minus 2. Hasn't changed since the last problem. This time now we have to derive x with respect to s. Well, this time we were told that x is the cosine of s, so if I derive that, now I actually do get something. I end up with the negative sine of s. Right. Again, the derivative of z with respect to y is the same as it was in the last step. It's x plus 3. And this time, if I take y equals sine of t, and I derive that with respect to s, I just get 0. So this gives me y minus 2 times the negative sine of s. Replace that y with the sine of t. So I get sine of t minus 2 times the sine of s. Maybe I'll put the negative on the outside. And that's the derivative of z with respect to s. I think the last big thing I have in this section is implicit differentiation, which you may remember as a topic from Calc 1, which is good. You should. It was done in Calc 1. Implicit differentiation is used when you have more than one variable in the problem. So look at that line that I put on the top. X to the third plus 3xy squared minus y to the fifth equals 0. Can you do this using methods you already know? Sure. Remember how to do this in Calc 1 terms. So what's my function? It's x to the third plus 3xy squared minus y to the fifth equals 0. So we did what? We took the derivative of the first term, which gave us a 3x squared. The second term required a product rule. So to derive xy squared, we took the first times the derivative of the second plus the derivative of the first, which was just 1 times the second. And there was something else that happened when we did it. Whenever we derived something with respect to y, we popped out a dy dx because that was the derivative of the inside. Some of you may have used y prime as your notation. That's okay too. Over here, when we derive y to the fifth, we're going to end up with a 5y to the fourth dy dx. All right, let's clean this up a little bit. So I get a 3x squared plus 3 times 2 is 6. So I have 6xy dy dx plus 3y squared minus 5y to the fourth dy dx. Then we collected all our dy dx's on one side, and we threw everything else that wasn't a dy dx over to the other side. So we threw out the negative 3x squared. We kept the 6xy over here. We moved over the 3y squared, which now became negative, and we kept the negative 5y to the fourth. And then we divided both sides by that item in parentheses. All right, so we divided both sides by whatever was in parentheses, and we came up with dy dx equals negative 3x squared minus 3y squared over 6xy minus 5y to the fourth. All right, my claim is that there's an easier way to do this. If you look back at my set of notes over here, using partial derivatives, you can find dy dx by taking the partial with respect to x and the partial with respect to y, dividing them and changing the sign. All right, so let's try it. Slide over here. The original function was x to the third plus 3xy squared minus y to the fifth equals 0. So I said, first step is take the partial derivative of f with respect to x. So that'll give me a 3x squared. If I take the partial with respect to x down here, then I just get a 3y squared. And the last term just becomes a 0. The partial with respect to y then, the first term is 0. The second term is going to be 2 times 3, so 6xy. Partial of that last with respect to y is minus 5y to the fourth. And then we're told just divide them and change the sign. So dy dx equals the opposite of 3x squared plus 3y squared over 6xy minus 5y to the fourth. To compare it, you're going to have to scroll way down because obviously this was a lot less work. Here, can I get them both almost in the same frame? There we go. So now you can compare my answer using partial derivatives up on the top with my answer using Calc 1 methods on the bottom. Will it work using Calc 1 methods? Sure, but just take the opposite of the partial with respect to x divided by the partial with respect to y, and you've got yourself a derivative. Why didn't we do that in Calc 1? Well, because we didn't know partial derivatives. But now we do. And that's the end of the section.